I'm so sorry for all the confusion this morning. As I said, I moved to the office to have some kind of quiet and focus, but then they were doing construction work just above my office and it was incredibly loud, so I had to run back home. But thank you for your patience. I actually managed to be on time. You guys can hear me well and can see my slides, just my slide, great. Okay, so thank you all for the invitation. Thank you for the kind introduction. I'm gonna start very far away. So at the very beginning, we are all babies, and at least this is something we're all gonna agree on. So we look around and we listen more or less casually to the surrounding voices and noises. We approach the people we like and avoid what we find scary. We touch and lick everything we can get our hands on. We move stuff from one place to the other and then just back for the sake of it. And then we point and we babble. And shortly thereafter, we start shooting questions as if there was no tomorrow. And then somehow, just over a couple of decades, babies turn into Brad Pitts, Madonnas, Simone Bileses, Nelson Mandelas, and Noam Chomskys, into aeronauts, researchers just like us, and plumbers and artists. So how does this happen? So let me see if I can set this up better with, okay. So humans are the only known system that develops into intelligent, sentient agents through playful exploration. Decades ago, Piaget theorized that children's exploration may be triggered and driven by a mismatch between what is expected and what is actually observed, which creates this uncomfort of uncertainty. So this cognitive disequilibrium, the wait, what moment, prompts children to resolve the discrepancy between what they think they know and what they actually encounter by searching for additional data, by testing our hypothesis and adapting or developing new conceptual structures that better accommodate the new information. And indeed, much of the cognitive developmental research in the last decade has been fueled by this metaphor of the child as a scientist, and has provided so far already robust evidence that children are not just curious and adventurous explorers, but purposeful, systematic, and effective information gatherers and active learners from a very young age. Now, children begin to distinguish between relevant and irrelevant information very early in life. For example, infants prefer to engage with a social partner who has demonstrated being informative and knowledgeable, and are more likely to attend, explore, and solicit information when they're presented with objects and events that violate their expectations and naive theory across different domains. And a growing body of research has also demonstrated that toddlers and preschoolers are more likely to explore when presented with confounded evidence. That is, when they're uncertain about the causal mechanisms at work or face evidence that really violates or contradicts their prior beliefs. Also, research shows that children's ability to make informative interventions to disambiguate the causal structure of a system begins to become more sophisticated in the preschool years. And this early developmental trajectory is echoed in work on selective trust, indicating that even toddlers ask and prefer to ask and query and trust the more reliable and knowledgeable sources of information. And similarly, finally, research has shown that preschool age children ask questions that are domain appropriate and informative, as opposed to redundant, uninformative, or irrelevant questions, and are able to reliably use the information they receive or independently gather to solve problems. However, other findings draw a way less optimistic picture, tracing instead a much more protected developmental trajectory, with children showing mature, adult-like active learning patterns only by late childhood or even later. For example, children do not begin to systematically generate from scratch, as opposed to identify the most effective questions, until age 7, and they do not demonstrate robust adult-like inquiry patterns until closer to age 10. So these results are in line with those from the decision-making literature, suggesting that children's pre-decisional information search, so the search preceding decision-making, is exhaustive, so that children tend to query all the available pieces of information, even when they are completely irrelevant. It's unfocused and highly unsystematic until age 10 or even later. And is also in line with some very pessimistic results from educational research, indicating that 6 to 12-year-olds often fail to demonstrate mastery of even the most basic scientific inquiry skills. So this is pretty puzzling. We have these two big bodies and pretty robust sets of results kind of contradicting each other, or at least really drawing diverging pictures and trajectories of developmental increase of competence and growth. So one way to reconcile this seemingly contradictory perspectives on the developmental trajectory of children's active learning could be to radically shift the theoretical perspective to focus on children's adaptiveness. That is, to acknowledge that the effectiveness and efficiency of children's, or adults for that matter, information search and hypothesis testing strategies, such as question asking and active exploration, cannot be measured in absolute terms. So the efficiency of a strategy crucially depends on the characteristics of the task at hand and the available resources, as well as on the learner's prior knowledge and expectations. So in the remainder of this talk, I will focus on what I consider one, if not the most crucial aspect of active learning, that is what I call ecological learning. That is the ability to explore and learn by exploiting the ecology, that is the particular structure and characteristics of a learning environment. And to do that, a child must detect these characteristics and dynamically adapt their exploratory and learning strategies to those characteristics to achieve and maximize effectiveness. So let me give you an example. This is Toma. Yesterday, Toma was late for school. Why was Toma late for school? So let's suppose we have these 4 possible reasons for Toma being late for school. So I tell you that these hypotheses are known to be all equally likely to be correct. So we can call this a uniform distribution. So suppose your goal is to find out why Toma was late for school by asking as few yes or no questions as possible. So questions I can only answer with yes or no. So think about this. What would you ask? Well, you could ask, is it because Toma couldn't find something? Now, this is a good question because whatever my answer is, yes or no, you will be able to rule out 2 of the 4 given hypotheses, that is half of them. This type of question is called constraint seeking and aims at reducing the space of possible hypotheses by testing features that are shared by several hypotheses. Now, let's suppose we have again these 4 possible reasons for Toma being late for school, but this time I tell you they're not equally likely to be correct. And we can call this a skewed distribution. So what would you ask now? Well, I hope you can see that now it's very tempting and it might make sense to test the most likely hypothesis directly because it offers a reasonable opportunity for a quick win. And at the same time, it does not partition the space in a much less uneven way compared to the best constraint seeking question one could ask in this situation. So this type of question is called hypothesis scanning. And hypothesis scanning questions are basically tentative solutions because once they get a yes answer, basically game is over, right? Now, because constraint seeking questions are able to rule out multiple hypotheses at each step of the search process, they are traditionally considered better than hypothesis scanning questions. However, as we have just seen in our example of the skew distribution, this is not always the case. Different kinds of questions are differently informative, depending on the likelihood distribution across the given hypothesis. And this can be generalized to all sorts of search and learning strategies. So this differential informativeness can be precisely calculated and formalized within computational frameworks. For example, as we do in terms of information gain. Information gain represents the reduction of entropy, that is, the reduction of uncertainty as to which hypothesis is correct. And I'm not going to get into more details here because the intuition of what this means would be enough to understand the remaining of the talk, but I'm happy to come back to this later on if you guys are interested in this. So today I'm going to give you an overview of the work my group has done and outline some of the new research directions we're currently exploring, starting with the core theme. So here we try to answer the question, are children ecological learners? And to do that, we measure the effectiveness of children's learning behavior in an objective, precise way, trying to quantify developmental differences using a variety of different paradigms, all under the same unifying computational framework. And this framework allows to operationalize developmental changes in active learning, focusing on this crucial aspect of effectiveness I mentioned earlier, that is adaptiveness, ecological learners. So in this first seminal study, we wanted to find out whether 7 to 10-year-olds and adults would be able to adapt the kinds of questions they generate from scratch to the likelihood distribution of the hypothesis space presented. So very similar to the example I introduced to you earlier. So we told participants that yesterday John was late for work, and we presented them with a set of 10 candidate reasons for why John was late for work, or could be late for work, in 2 different conditions. And they had to find out why John was late for work by asking as few yes/no questions as possible, really just like an example before. So in the uniform condition, hypotheses were all equally likely, or a list that were presented as such. And here asking an hypothesis scanning question would require to randomly select an hypothesis to test first. So in this sense, asking a constraint seeking question would always be more efficient. In the skewed condition, however, some hypotheses were presented as more likely than others, such that hypothesis scanning questions could target what were defined and described as the most likely options, being almost as efficient as constraint seeking questions, while also offering the chance of a quick win. So really, much like the example we played earlier. So here's what we found. We found that all participants asked a higher proportion of constraint seeking questions in the uniform distribution condition in yellow here, compared to the skewed condition in red. So participants were all more likely to ask hypothesis scanning questions when there was one more likely hypothesis that could be targeted first. And we can also see that although adults overall asked a higher proportion of constraint seeking questions compared to children, they did not adapt their question asking strategies more promptly, as is indicated by a similar magnitude in the difference between the 2 conditions in each age cluster. So overall, the seminal work demonstrated that by age 7, children are ecological learners. So they dynamically adapt the types of questions they ask to improve efficiency, and they do that as promptly as adults. Now, what about younger children? Previous research shows that although even 4-year-olds are able to spontaneously generate constraint-seeking questions, those constraint-seeking questions they ask are often not the most efficient available. Now, asking questions has 2 components, a generative component and the selection component. The generative component refers to the ability to come up with reasonable, good questions from scratch, whereas the selection component refers to the ability to select the best among self-generated or given alternative questions. So in this project, which is a collaboration with Zilim Sim at Berkeley, we tried to isolate the selection component from the generative component of asking questions to investigate whether 5-year-olds will be able to identify the most efficient between two given questions, although they're not able to generate the most efficient questions from scratch just yet. So children were presented with a storybook describing the reasons why Toma, whom we're now familiar with, was late to school over several days. So in one condition, children were eventually presented with a uniform hypothesis space where Toma had been late for school always for a different reason. Whereas in the other condition, children were presented eventually with a skewed hypothesis space where Toma had been mostly late for school because he woke up late. Now, then they were told that today Toma was late for school again, and that his monster friends, Dex and Wug, wanted to find out why. And basically each of these two monsters' friends got the chance to ask one question to be able to find out why Toma was late for school once again. And in each condition, one of the monster friends asked a constraint-seeking question, and the other one, an hypothesis-scanning question. And children had to say which of the two monster friends they thought would find out first why Toma was late for school. So basically, they had to identify which of the two questions they were presented with was the most informative. Crucially, in the uniform condition, the constraint-seeking question asked was more efficient, whereas in the skewed condition, the hypothesis-scanning question was more efficient. Does this make sense? Some nodding over there. So as hypothesized, we found that the majority of children in the uniform condition were able to correctly identify as more efficient the monster asking the constraint-seeking question, in yellow here again, whereas most children in the skewed condition selected the monster asking an hypothesis-scanning question. So using a different paradigm based on exactly the same computational framework from the previous study, we were able to show that despite not being able to generate the most effective questions from scratch just yet, even 5-year-olds already have the computational foundations for developing successful question asking strategies. They adapt their reliance on different kinds of questions based on the hypothesis space presented, so they are ecological learners. And we also performed a bunch of follow-ups showing that this adaptation is guided by information gain and not by simple or simpler heuristics based on more superficial cues, such as the frequency of the presented hypothesis or the number of different hypotheses each question targeted. What about even younger children? So question asking paradigms have obvious limitations when trying to study toddlers. And that's why it took us so long to find a way to test the emergence of ecological learning in even younger, potentially pre-verbal children, or just at the beginning of their verbal life children. So in this project, which is a collaboration with Nora Svoboda, a PhD student of mine, we moved away from a verbal paradigm, keeping pretty much intact the theoretical framework, to investigate whether younger children, 3- and 4-year-olds, adapted their exploratory non-verbal strategies to the likelihood distribution of the hypothesis space presented. So we presented children here with 2 large boxes, one black and one white, both containing 2 smaller colored boxes, and with a small egg shaker, which could be used to activate this amazing magic machine. So there were 2 training phases. During the distribution training phase, the experimenter placed the egg shaker in one of the 4 small boxes 4 times. In the uniform condition, the experimenter always placed the egg in a different small box, whereas in the skewed condition, she always placed the egg in the same small box. And after each placement, children were asked to retrieve the egg and use it to activate the magic machine so that we could make sure they had followed the entire procedure. After this training, children were demonstrated 2 actions that are useful to find out whether a big box contains the egg shaker. One can shake the box to hear whether the egg shaker is in one of the 2 smaller boxes contained, or one can open the big box to see whether the egg is in one of the 2 smaller boxes inside. So one opens the big box, open the 2 smaller boxes, and then you can just like have visual access to the contents. At test, children were asked to close their eyes, and the experimenter hid the egg once more, and then children were asked to open the eyes and look for it. Crucially, children were told that they could open only one big box. So here's the idea. Shaking the box kind of corresponds to a constraint-seeking question. So if you don't know where the egg could be, as in the uniform condition, then it makes sense to first shake the box so that you know which big box you should be opening, because you can open only one big box. And in this sense, you wouldn't want to risk opening the wrong box, right? However, if you do know where the egg is hidden, because the experimenter always hid it in the same place, then you could just go and open the big box, and then the small box where you know the egg can be found. And this kind of corresponds to an hypothesis scanning question. You have a strong intuition of what the solution is, and you just go for it, taking the chance for a quick win. Does this make sense? So here's what we found. Again, same color coding or similar color coding. We found that 3- and 4-year-olds were more likely to perform the shaking, constraint-seeking action in the uniform condition in yellow here, where it was necessary to resolve the uncertainty as to which large box should be opened, as compared to the skewed condition in red, where they knew where the egg was hidden and could therefore bet on a quick win. So in this sense, we were able to show, using exactly the same computational framework, that even 3- and 4-year-olds are ecological learners. They use different exploratory actions depending on the information structure of the task at hand. Sorry. Now we are up for the challenge of developing a paradigm that allows to investigate the emergence of ecological learning in infants. So previous work has demonstrated that from early on, infants show simple, meaningful forms of active learning. We have seen some of this work this morning and a couple of days ago. So for example, we know that infants can tailor their attention depending on stimulus informativeness, disregarding stimuli that do not offer an opportunity for learning. And we also know that infants learn more from objects that violate their expectations, and they tend to explore this violating expectations objects or situations more and more often. We do not know, however, to what extent infants are adaptive learners. So in this work, which is a collaboration with Francesco Poli from the Dunder's Institute, we took the same framework that I've illustrated so far and developed a new gaze contingent paradigm with very low task demands to investigate whether infants would be able to adapt their search to the likelihood distribution of the hypothesis. So let me lead you through this paradigm. Infants, we're talking here about 12 to 24 months old, are presented with this scenario. So 4 differently colored areas, just like in the boxes before, and a cute animal appearing on a trampoline on the bottom of each of this 4 colored areas. So the animal jumps up with this jumping sound and disappears from the screen for 2 seconds. Then it comes again, picking in, rotates, and disappears with this super annoying sound, which is apparently very engaging for infants. So this happens 8 times, and we manipulate across infants, whereas the animal always hides in a different place in the uniform condition, or whether it most often hides in the same colored area in the skewed condition. So this should all sound very familiar by now. Importantly, trial after trial, the screen turns darker and darker so that the infants become progressively aware that their look controls a torchlight that is able to shine in the dark. So after the 8th trial, the screen turns completely dark, and then we move to the test phase. So infants hear the jumping sound, but they don't see the animal. So they know it jumped high somewhere because of the sound, and they want to be there waiting for it when it picks out, because it's only going to stay out for a second. But where should they look? Now, the idea is that infants in the skewed condition will just wait where the animal has almost always jumped, say in the blue area. However, infants in the uniform condition really have no idea where they should look, right? So they should be more likely to look for cues in the waiting time, looking for the trampoline. So in this way, they would know where to wait for the animal picking in. So this is a pretty ambitious study, we know this. We have collected a bunch of pilot participants so far, 12, and pilot results do indicate that infants indeed perform differently in the two conditions. So in the uniform condition, infants spend more time searching in the correct target location. In the skewed condition, they spend more time waiting for the animal appearing in the correct target location, the one they have learned during familiarization. Conversely, in the uniform condition, they are more likely to spend time searching for the informative cue elsewhere on the screen. And these preliminary results suggest that infants can adapt their information search in an active way, depending, in this case, on the probabilistic structure on the environment. So it looks like we might indeed find that infants are already ecological learners, so that they are able to strategically rely on different search patterns depending on the structure of the environment and the problem they're presented with. So overall, altogether, this series of studies demonstrates that efficient adaptive search strategies emerge much earlier than previously assumed. And in this sense, these findings also highlight the importance of developing age-appropriate paradigms that really are able to capture children's early competence to gain a more comprehensive and fair picture of their active learning abilities. Also, this work offers a process-oriented theoretical framework that can really try to accommodate and reconcile this growing but still sparse body of work documenting children's active and adaptive learning. And in the last couple of years, this approach allowed us to demonstrate that young children adapt their exploratory strategies to other characteristics of the problem space considered as well, such as causal sparsity, that is, the number of causes impacting the system or goals. So a couple of students in my lab are mostly focusing on exploring ecological learning and the emergence of ecological learning across different domains and in different problems. So the work I presented to you so far illustrated how this computational framework we adopted allowed to quantify and measure and capture the developmental trajectory of active and ecological learning. But beyond this, this framework can also open the way to study developmental changes from a more process level, deeper and richer perspective. For example, allowing to deconstruct and disentangle the mechanisms underlying developmental differences, to identify the contributions of individual, age-related, and environmental factors to active learning, and to capture what drives children's curiosity and persistence. So let me give you a couple of examples here. So foraging for food, developing new medicines, learning complex games are search problems with vast, potentially infinite numbers of possible actions. And under real world time or resource constraints, exhaustive exploration is impossible. and optimal solutions are generally just unobtainable. So how do children and adults learn which actions to take when not all outcomes can be explored? That is, how do they balance the exploration-exploitation dilemma? So on the one hand, we want to explore unfamiliar options that can provide us with useful information for future decisions. However, they may result in poor immediate rewards. On the other hand, we want to exploit options we know are highly rewarding, but this often implies giving up on learning about unexplored options, which could potentially be even better. So a key finding in the psychological literature is that children tend to try out more options than adults. And this has been interpreted as evidence for higher levels of random exploration in children. So according to this interpretation, children have higher temperature parameters. And this means that they initially sample very randomly across a large set of possibilities before eventually focusing on a smaller subset. And this temperature parameter is then expected to cool off with age, leading to lower levels of random exploration in later childhood and adulthood. However, there is another potential explanation for developmental differences in search. After all, as we've seen so far, children are definitely not random. They're clearly capable of exploring their environment in a systematic, meaningful fashion. So developmental changes in the variability of sampling could also be explained by changes in directed exploration. So in this sense, children's search appears more scattered, but only because they're more likely to seek highly uncertain options in order to gain more information and reduce uncertainty about the environment, and then learn. A third possibility is that rather than explaining development as a change in how we explore, developmental differences in sampling could be explained by a refinement of cognitive processes leading to a broader generalization. That is, development may be associated with a more fine-grained ability to generalize beyond observed outcomes, therefore guiding search by forming inductive beliefs about novel options. So in this project, in collaboration among others with Björn Meda, we tested the individual contribution of these three mechanisms, which are not mutually exclusive, as they correspond to the three parameters of our model, theta, beta, and lambda. So we used a spatial search task in which 7 to 11-year-old children and adults were presented with a grid like this one. So initially, a single tile was revealed, and participants were given a limited number of clicks to acquire as many points as possible. And rewards were spatially correlated, with nearby tiles having more or less similar rewards, where the patches are identifiable by color. So this spatial structure of the environment provides traction for generalization, which can be used to guide search and can support this generalization more in the smooth environments, more predictable on the right, or less, as in rough environments, less predictable on the left. So here's what we found. We found that adults in gray here gained overall higher rewards than children. So overall, achieved better performances. Also, adults exploited more strongly. That is, they were more likely to re-click on the same tile, which is this bar here on the left of the red line. Whereas children were more likely to sample unique options, thereby gaining overall lower rewards, but exploring the environment more extensively. What is more important is that using a computational model, as I mentioned before, with parameters directly corresponding to the three hypothesized mechanisms of developmental change, we found that children generalize less from observed to unobserved tiles compared to adults, and they rely on uncertainty-directed exploration more than adults. But we did not, however, find differences in random sampling. So overall, our results shed a new light on the developmental trajectories in generalization and exploration, casting children not as merely prone to more random sampling behavior, but as directed explorers who are hungry for information in their environment. And using the same paradigm, we recently also tested 4 to 7-year-olds and found that although younger children do tend to be more random in their search compared to older children, after all, even 4-year-olds can show pretty strong and robust uncertainty directed exploratory patterns. When trying to deconstruct the mechanisms underlying developmental differences in active exploration and learning, it is also crucial to identify the task-related, environmental, and individual factors potentially responsible for this observed developmental changes, supporting or constraining children's search and learning. So in collaboration with Costanza De Simone, a PhD student of mine, we developed a battery of tests to comprehensively assess 6 to 12-year-olds children's active learning performance. So the battery includes a bunch of tests, some of which I've already introduced in this talk, which measure different aspects related to active learning: effectiveness, adaptiveness, speed, accuracy of learning on a wide range of tasks: question asking, question evaluation, spatial search, so the grid task is included, evidence selection, functional learning. And this battery allows us to examine the link between the efficiency of active learning strategies and their actual effectiveness, as measured in terms of learning success and accuracy. Moreover, it helps identifying performance differences and dependencies across different learning tasks, answering questions such as, do children who perform better in spatial search tasks also are asking more informative questions, or are the two things completely independent? So overall, this battery aims to establish something like an individual index for learning potential that captures children's more general ability to search and learn effectively and adaptively. We also administered children a battery of tests to assess a comprehensive set of cognitive abilities, from vocabulary to working memory, as well as their attitude towards learning and some personality traits. So this battery allows to examine whether and to what extent these factors impact and contribute to the effectiveness and success of children's active learning strategies across different tasks, identifying key sources of developmental change and inter-individual variability. And finally, we administered these two batteries in several different countries: Germany, Cuba, Egypt, India. And this cross-cultural replication allowed us, on the one hand, to obtain a much higher variability in our sample, especially in terms of SES, parental education, schooling styles, but also obviously allowed us to add the cultural and environmental factors as potential predictors of active learning more generally. Now, here is the bummer of this talk. We don't really have yet conclusive results, so we're still currently analyzing the results using structural equation modeling. But preliminary analysis do indicate similar active learning performance across countries, indicating in this sense a general robustness of active learning across cultures and environments, and in particular strongly suggests that active learning is a predictor of academic achievement, even after controlling for other cognitive factors. But crucially, our results strongly, robustly suggest that SES, so socioeconomic status, does not impact active learning potential, which is quite comforting, I think. But moving on, why do children explore in the first place? So what drives them and makes them persist? So this is one of the greatest challenges for artificial intelligence, that is how to behave adaptively in scenarios with sparse or no rewards. So in this project, which is a collaboration with Eric Schultz, we investigated whether and to what extent the opportunity to get information systematically motivates young children's exploratory actions. That is, whether expected information gain, the same information gain we have considered in the previous studies, serves as an intrinsic reward strong enough to drive exploration and learning. So in 2 studies, we measured 24 to 56-month-old children's persistence in a game in which they had to search for a cartoon animal hidden behind a series of closed doors. So crucially, we manipulated the degree of uncertainty about which specific animal participants were searching for. That is, we either told children which animal they were searching for example, the lion, or we told them that it could be one of 8 different animals, so that finding the hidden animal gave children information about its identity in addition to discovering its location. And although the animal was never revealed, regardless of the time children spent searching, our results indicate that children were more persistent in their search in the 8 animals condition, in orange here, when there was higher uncertainty as to which animal they would find, and therefore more information to be gained. So they also opened more doors on average. They searched for a longer time, and more of them endured and kept on opening doors until the end of the game. So overall, these results indicate that in absence of any external rewards, toddlers and preschoolers search is motivated by the expected informativeness of the actions that can be performed, highlighting the importance for research on artificial intelligence to invest on curiosity-driven algorithms. And I'm gonna maybe come back to this at the end of my talk, depending on the time. So this developmental and computational work I have presented generates insights and offer methods that can also enrich and deepen our understanding of children's social learning. And here is one example of this more recent line of work. So even young children strategically choose to learn from those they identify as good teachers, the most trustworthy, helpful, knowledgeable informants. We have seen some of this literature reviewed also in previous talks during this workshop. However, beyond the knowledge and confidence people exhibit, the origins of this knowledge can also have implications for their reliability and trustworthiness. For example, someone who acquired knowledge through their direct experience may have a deeper understanding than someone who acquired the same knowledge through someone else. So in this study, a collaboration with Sophie Bridgers, we investigated whether 3 to 8-year-old children are sensitive to the process by which agents come to know what they know. So children were presented with 3 videos of 3 learners figuring out how to activate this toy that we call the original toy. So all 3 learners eventually demonstrated to know how to activate this toy, but they differed in how they acquired this knowledge. So the active learner figures out how the toy works all by herself. The instructed learner does play with the toy, but someone else shows her how it works. And the passive learner just watches someone else figure out the toy, does not even get a shot. At test, children were presented with the original, a similar but slightly more complex, and a completely different toy, and could choose one of the 3 learners to help them figure out how they work. Now, what would we expect here? So who would you go for when trying to figure out the original toy? Well, for the original toy, it doesn't matter, right? Because all learners eventually demonstrated to know how to activate this one toy. So all of them can help us. But what about the similar toy? Well, here we predicted that children would prefer the active learner because she's the only one who demonstrated competence in independently figuring out similar toys. And what about the different toy? Well, this is more tricky because it depends on whether children would generalize the competence demonstrated by the active learners to different kinds of toys as well. So it depends on how conservative their inference is. Now, I'm not going to get into the details of this long study. Also, there's a bunch of studies we have done on this line trying to identify the cues children are basing their inferences on, but the main result is that children preferentially seek help from an active learner, but only on similar problems. So in this case, only on the similar toy, where the active learner's competence was clearly relevant, indicating that young children understand that the process of active learning, how you come to know your active learning abilities also matters, and not just what you know. And these results, I think, are super interesting because they suggest that children may be able to disentangle to a certain extent between someone who knows things, an expert, and someone who maybe is not knowledgeable, but is competent in learning about new things. For example, is good at asking questions. So this tension, knowledgeability and learning potential, is really one that interests me a lot. So we have just started scratching the surface. For example, in a recent study we just published with Costanza, we found that older children and adults, but not younger children, seek the help of an expert when the task they're presented with is related to their area of expertise, but they seek help of a good question asker when the task is outside the other agent's area of expertise. So it seems that this may not develop very early on, but maybe it was not the right task to check the emergence of this intuition. It was very strongly relying on verbal abilities. So this is just a line of work we're really doing a lot of new experiments on. So I think I have a couple more minutes.
5 more minutes, yes.
Yes, great. That's all I need. So I want to conclude telling you a little bit about the perspectives and methodological tools I think this kind of work offers to support and evaluate the design of more applied interventions aimed at boosting children's learning success in classroom settings and beyond. So one way to do this is, to develop interventions that enhance children's learning performance by supporting the effectiveness of their active learning strategies. For example, helping them to ask more informative questions. So previous attempts to improve children's question asking strategies have achieved only moderate success. Most children did not improve their performance at all over time, and the modest training benefits when present never generalized to other sets of stimuli or domains and were no longer apparent 1 week later. However, our group has recently demonstrated that it is indeed possible to somehow support children's question asking performance even without extensive training. For example, by prompting children to explain previous observations related to question asking problem spaces, or by providing them with the verbal support, for example, the category labels they can use to ask more effective constraint seeking questions, or by presenting them with spatial search tasks instead of verbal tasks. Another way to support children's active learning is to design learning environments that just enhance their performance. And this series of projects, and this is the last series of projects I present today. It was a lot, I know, all in collaboration with Doug Markant. So children were here asked to play a simple memory game where they had to remember 64 objects. So for half of them, children could decide the order and pacing of study. And for the other half, they could just passively observe the study decisions of a previous participant. So basically, they were just watching the videos of other children studying those objects. And at test, children had to identify the objects that studied earlier from among a set of distractors. We found that recognition memory was more accurate for objects studied in the active as compared to the passive condition. So the red line here compared to the blue line, even after a week-long delay. And we replicated this effect in different versions of the task across samples from different countries, with adolescents, with elderly adults, with children affected by autism. And now we started testing even infants using an eye tracking version of this paradigm. And it seems that even infants show a benefit of active control of study compared to passive study. So in this sense, our results do suggest a strong robustness of the advantage of active learning that could be exploited in educational settings. So I'm going to skip this slides that we're just like outlining the work we're currently doing. And I'm going to conclude saying that I hope I convince you that looking at ecological learning is that ecological learning is an interesting perspective, and it's a good way to look at the mechanisms underlying and driving developmental trajectories and explorations, because it gives us the opportunity to really look at children as motivated and curious learners who are, yes, hungry for information in their environment, but also sensitive, selective, effective, and above all, adaptive. So way more sophisticated than previously thought. And I want to thank you for your attention, and I really welcome all the questions you might have. And I want to thank my collaborators and the members of the iSearch lab and our institutional partners. Thanks.